Hello guys, welcome to applications of differential equations, and today we are looking at a mixture problem given to us. So there are different kinds of application of differential equations, and we are going to be seeing them in this series of applications of differential equations. So for today's, we are dealing with a mixture problem. So this is how a mixture problem looks. Now in problem 1, we are given that a tank initially contains 120 liters of pure water. So a mixture containing a concentration of gamma grams per liter of salt. Okay, I need to emphasize something over here. So this is gamma, okay, gamma, that's the Greek symbol. Now, a mixture containing a concentration of gamma grams per liter of salt enters the tank at a rate of 2 liters per minute, and the well-stirred mixture leaves the tank at the same rate. Okay, let's take note of this. Now, find an expression in terms of y for the amount of salt in the tank at any time t. Also, find the limiting amount of salt in the tank as t approaches infinity. Okay, let's dive into the solution of this problem. Okay, now in solving this problem, I want us to take note of a couple of important points. Now, this is a mixture problem, okay, and there is a fundamental formula that we use in tackling mixture problems, and the formula is given to us as the rate of change of quantity, okay, of salt. That's y prime is given to us as input rate minus output rate. Okay, so I'm just going to establish some important formulas that you need to be solving mixture problems. So y prime in this case is not dy dx. Actually, y prime is dy dt. Is that okay? So this is the context we are looking at. Rate of change is usually with respect to time. Now, the next, or the rate of change of y, which represents the amount of salt in the tank at any time. So y represents the amount of salt in the tank at any time t. Okay, so take note of that. So the rate of change of this amount of salt is given to us as the input rate minus the output rate, the input rate minus the exit rate. Now let's take a closer look at what the input rate is. To evaluate the input rate, you're going to use this formula. The input rate is given to us as the input flow rate, times input concentration Is that okay? So the same thing applies to the output rate. The output rate is given to us as the output flow rate times output concentration. Okay, so now let's use these formulas and see how they look like. Now, to get our input rate, we're going to take the input flow rate. So the input flow rate is given to us as the rate at which a mixture, okay, containing a particular concentration enters the tank. Now the input flow rate is given to us as this value over here, 2 liters per minute. So we have 2 liters per minute. Okay, so this is the input flow rate times the input concentration. Now a mixture containing a concentration of gamma grams per liter. Okay, so we have gamma grams per liter. Okay, so when you evaluate the input rates, liter cancels out liter, and what we are left with is 2 gamma gram per minute. Okay, so this is the input rates. Okay, the input rates. So this is how the input is changing, 2 gamma grams per minute. Now we'll go ahead and evaluate the output rate. So in the output rate, what is the output concentration? Now take note of what was said in this particular place. Now the well-stirred mixture, after this mixture containing a concentration of gamma grams per liter of salt enters the tank at this particular rate, the well-stirred mixture leaves the tank at the same rate. It's trying to tell us that the output flow rate is still equivalent to the input flow rate, and the output flow rate is just going to be 2 liters per minute. Now the fact that the output flow rate is equal to the input flow rate has a lot of implications, and one of the implications which we are going to be working with is that the original volume, okay, or the original volume of water in the tank will remain the same. Since the input flow rate is equal to the output flow rate, the original volume of water in the tank will remain the same. That means there is actually no net change. So the volume in the tank is always going to be 120 liters, as we can see in the question. Okay, so the volume of liquid in the tank is going to be what? 120 liters, since the input flow rate and the output flow rates are different. So later in the future, I'm going to solve a problem where the input rate and the output rates are not the same, and you're going to see how we're going to tackle that problem in that case. But for now, let's deal with the case where the input and the output flow rates are the same. Now that we've determined the output flow rate, what is the output concentration? Okay, follow me carefully on this one. Now we have that concentration is always given to me as quantity of concentration is given to us as some mass over some volume. Is that okay? So this is the way we are trying to express the concentration, some mass over some volume. Now check out the fact that a mixture containing gamma grams per liter of salt enters a tank at a particular flow rate. So the well-stirred mixture leaves the tank at the same rate. So how do we determine the concentration of the output? Well, we determine the concentration of the output by assuming that, okay, after the mixture is stirred in the body of the tank, there will be y grams of salt. Okay, there will be y grams of salt. So there will be y grams of salt. So the next question is in what volume will these y grams of salt exist? Remember, concentration is the amount of salt over the volume. So we are assuming that there will be y grams of salt. This time around, y is an unknown, so we will have y grams of salt, and the volume that we are going to be dealing with in this time around is 120 liters. So why is it 120 liters? Because remember, we established that since the input and the output flow rates are the same, that means the volume in the tank initially will not be altered. It will always be 120 liters. Okay, so you can expect that to calculate the concentration of the output liquid, you can take it as the assumed volume, the assumed mass of salts in the body of the container, which is y grams, to the overall volume in the tank, in the body of the tank, which is 120 liters. So this is how we are going to be calculating the output concentration. So you're going to always calculate it as an unknown percentage of salt, percentage by mass of salt, which is y, divided by the net volume in the tank. So 120 liters. So if the input flow rate and the output flow rate are the same, then the volume that you're going to use here is always going to be the original volume. If the input flow rate is bigger than the output flow rate, that means the net volume would have increased, right? So if the output flow rate is bigger than the input flow rate, that means the net volume would have decreased. Okay, so just take note of some of those terminologies and let's proceed with what we have here. So if we evaluate this particular one, liters cancels out liters, and what I now have is 2y over 120 grams per minute, and this simplifies to y over 60 grams per minute. Now the differential equation that we are going to arrive at when we substitute the input rate and the output rate in equation 1 is y prime is equal to input rate 2 gamma, where gamma is a constant, we don't know what gamma is, then minus the output rate, which is y over 60, okay, grams per minute. Is that okay? So if I transform this differential equation, I'll be having y prime plus y over 60 is equal to 2 gamma. Okay, so this is equation 4. So this equation 4 is now a linear differential equation. So this is a linear differential equation because it's actually in the form y prime plus p y is equal to q. Okay, so I hope you still remember the tricks for solving linear differential equation. So for solving linear differential equation, we have our integration factor to be exponential integral of p, okay, dt, because we are no more dealing with x this time around. We are dealing in the time domain, so the independent variable of our integral is actually t. So this is our integration factor, and therefore our solution will be y times integration factor is equal to integral of q times integration factor then dt. So these are the formulas we are going to use to attack this problem over here. So let's dive in. So y prime is still as good as you saying dy dt. Then permit me to do some separations. This is 1 over 60, then y is equal to 2 gamma. Is that okay? 5. So from this equation, my p is 1 over 60 and my q is 2 gamma. So I'm just going to use the formula for integration factor, which someone can still call a mu of t, and this is an exponential integral of p dt, which is exponential integral of 1 over 60 dt, which will give me exponential 1 over 60 integral of dt, and which will give me exponential 1 over 60 multiplied by t. Don't put the integration constant, which is exponential t over 60. Is that okay? So our integration factor is exponential t over 60. So our solution from the formula is y multiplied by integration factor is equal to integral of q, which is 2 gamma, multiplied by integration factor, which is exponential t over 60, then dt. So if you solve this problem, we'll have y multiplied by exponential t over 60 is equal to, removing the constant, you have 2 gamma integral of exponential t over 60 dt. Now you're going to use this identity to integrate an exponential at respect to t, and you get exponential at over a plus c. Okay, whatever is here is going to come down here. So let's see how to integrate it. So y exponential t over 60 becomes 2 gamma, then integrating exponential t over 60, we'll have exponential t over 60 divided by 1 over 60. Is that okay? Then plus constant of integration. Now if you rearrange y exponential t over 60 will now be equal to 2 gamma, then you have 60 over 1 exponential t over 60 plus c. Is that okay? So when you do 1 divided by a over b, you actually get B over A. So that is what is playing out in this particular place. And I hope we know why I have 2 gamma exponential t over 60 divided by 1 over 60. Exponential t over 60 is still the same thing as exponential 1 over 60 t, and when you integrate it according to this rule over here, when you're integrating exponential at, you have exponential at over a, so a comes down, and in this case our a is 1 over 60, so we'll have exponential 1 over 60 t divided by 1 over 60, okay, plus c. So that's the reason why this line is like this. So when we continue, we'll have 120 gamma exponential t over 60 plus c, and this is why exponential t over 60. So by the time we divide through by exponential t over 60, we'll get y is equal to 120 gamma exponential t over 60 plus c divided by exponential t over 60. This gives me, distributing the denominator, you have 120 gamma exponential t over 60 divided by exponential t over 60, then plus c divided by exponential t over 60. So exponential t over 60 takes out exponential t over 60, and what you're left with is y is equal to 120 gamma plus c exponential minus t over 60. So the law of indices is 1 over exponential a is equal to exponential minus a. Okay, so that is the rule that we are using from this point over here to this point over here. Okay, so let's keep going. Now having gotten up to this point, we now want to find what and what exactly. So remember that the question asks us to find an expression for the amount of salt in the tank at any time. So this is the expression for the amount of salt that will be contained in the tank at any time. Amount of salt in the tank at any time, and it has a unit in grams. Is that okay? So amount of salt is actually measured in grams, so that will be what we'll be dealing with. So they asked us another question, and let's quickly see what that question is. So in the other question that we were asked, let me just scroll up quickly. We were asked what? Okay, find an expression for in terms of y for the amount of salt in the tank at any time. Find the limiting amount of salt in the tank as t approaches infinity. Okay, so let's head back to where we stopped and solve. So now that we want to find the limiting amount of salt as t approaches infinity, one thing we should do is we should first of all determine the integration constant. Okay, let's determine the integration constant. C. How do you determine the integration constant? By initial conditions. Okay, so in this kind of problems, initial conditions can be extracted from the question. Now the initial condition we are going to be working with is, you ask yourself, at the time when perhaps this mixture had not started, what was the amount of salt in the tank? What was the amount of salt in the tank? If you ask me, I'll said the value of salt in the tank was 0 when t was equal to 0, and if you ask me why, I'll show you. Let's get back to the question. So this is the question, and from the question, what can you see? You can see that a tank initially contains 120 liters of what? Pure water. This is pure water. So the body of the tank was initially pure water, and there was no amount of salt present in the tank initially. Is that okay? So you can agree with me now that y initially, which is the amount of salt, or y naught, which corresponds to y of 0, okay, or y when t is 0, is equal to 0, because there was no salt initially, since the tank initially contained 120 liters of pure water. Is that okay? So our initial condition, when t is equal to 0, our y is equal to 0. That means there was no salt. Please be reminded that y represents the amount of salt, okay, amount of salt, and I emphasize it over and over again. So using that, we are going to solve this problem, and let's see what we get for the constant of integration. Now, substituting this into this particular equation over here, 0 is equal to 120 gamma plus c exponential minus 0 over 60. So what I just did was, anywhere you see y, you put 0, and anywhere you see t, you put 0. So solving, you will have 0 is equal to 120 gamma plus c exponential 0. Okay, 0 over anything is 0, and 0 times any sign is still 0. 0 swallows up pretty much everything. So exponential 0 is equal to 1. So if you calculate the value of c from this, you're going to get c is equal to 0 minus 120 gamma, which is equal to minus 120 gamma. Okay, so this is the value of c. So the differential equation, okay, or the expression for the amount of salt present in the tank at any instant of time is 120 gamma, then minus 120 gamma exponential minus t over 60. So this is actually the amount of salt in the tank at any time. So this one was general solution, or primitive, but this one is the exact or particular solution. So we have particular solution. So we're going to be working with this one. Okay, so what I just did was, to get this particular equation over here, I just replaced c with its value, which is negative 120 gamma. Now you can still simplify it and make it like this: 120 gamma into 1 minus exponential minus t over 60. So this is a pretty much cooler form of simplifying your answer, since 120 gamma is common in both terms. So the B part of the question is the limiting value of salt in the tank as t approaches infinity. So this is just very easy, like easy peasy. So the answer will be limiting value of y as t approaches infinity, which evaluates to 120 gamma into 1 minus exponential negative infinity over 60. So let's examine exponential minus infinity over 60. Now exponential minus infinity over 60 is still exponential minus infinity, because infinity is a very large number, and when you divide infinity by something like 60, it doesn't really matter, it's still going to be infinity, it's still very large. And exponential minus infinity actually tends to 0. Why does exponential minus infinity tends to 0? According to the law of indices, exponential minus infinity is 1 all over exponential infinity. Is that okay? And exponential minus exponential infinity itself is a very huge number. So they are trying to tell me that this denominator over here is going to be exceedingly large, because you're taking exponential of an exceedingly large number. And when you do 1 over exponential, an exceedingly large number, you're going to get approximately 0 or 0.000 something, and so on and so forth. So just know that exponential minus infinity goes to 0. Okay, in another future video I'll explain this more, show more emphasis on this. So they're trying to tell me that this particular place actually wraps up to 0. So what we are going to get is that the limiting value of y as t approaches infinity will be 120 gamma of 1 minus 0, since exponential minus infinity is 0, and this is 120 gamma. and remember to put the units grams. So this is the answer, 120 gamma grams. So this is all about this problem, and as you can see, it's actually an application of first order linear differential equations. So for mixing problems, remember the key is to make this statement that y prime, or the rate of change of amount of substance, which is salt in the tank, is input rate minus output rate, and input rate is input flow rate times input concentration, output rate is output flow rate times output concentration. And remember that when the input flow rate and the output flow rates are the same, then the amount of liquid in the tank, or the volume of liquid, will always be equal to the initial volume of liquid. But if the input flow rate is greater than the output flow rate, for instance, then the amount of liquid in the tank will be increased. However, if the output is greater than the input flow rate, then the amount of liquid, then the net amount, that's what I'm talking about, will actually decrease. So I hope to solve a problem later on a question where the input flow rate and the output flow rates are different. And if you want to see that, just post something in the comments and I'll quickly respond and make a video on that. Okay, so I hope you've understood how to solve this problem, and next video we're going to be seeing another application of differential equations. So stay tuned, please subscribe and share to your friends, hit the notification button so that you can be updated as we learn ordinary differential equations and engineering mathematics together. So thank you very much. Engineering mathematics to the world.